Yeah, here you go. Okay, March 4, 2026, right? And that's on Wednesday. Let's take a look at the schedule as well. We are writing here Wednesday, 4th of March. And we're going to cover some of the material for the exam, right? That's going to show up in the exam. And then the exam is going to be next week, 7 days from now. 7 days from now, it's going to be from 8:50 a.m. to 10:50 a.m. in Canvas. And okay, what we want to do, we want to finish covering chapter 19. Okay? Here you go. Yeah, chapter 19. The second part of 19.5. The second part of section 19.5, dielectrics and capacitors. All the equations, okay? All the equations that we derived the last time on the capacitors, okay, relates only to capacitors having vacuum, having the vacuum between their plates, okay? So this equation here is the capacitance of the capacitor in which the space between the plates is just vacuum. It's just vacuum, okay? But then what happens? So what happens if we insert a different dielectric in between the plates? Okay, what happens? And that's what you are going to cover. That's what we're going to cover today, okay? And you're going to need some illustrations right in here. Different dielectrics between the conductors of a capacitor. So remember, two metal plates, one positively charged, the other negatively charged. Whenever you have a vacuum, and even air, not just vacuum, but air as well, the electrical properties of air is somewhat similar to the electrical properties of vacuum. And the capacitance ends up being what we calculated before. This equation that you see right here, okay? And now at this point in time, again, you must imagine, you must visualize that you have these lines of electric field between the two capacitors going from the two plates. Not the two capacitors, right? It's two plates. The two plates form a single capacitor. So the electric field lines are uniform electric field lines, points from the positive charge to the negative charge. And those vectors, those arrows, are the best way to visualize the electric field, to visualize an invisible entity, right? An invisible quantity that we call the electric field. That's why you need some imagination here to visualize difficult stuff, right? So that's what we get when you have vacuum or air between the plates. Now, suppose that we insert between the plates something else like a piece of cardboard, some dielectric. Can be a piece of cardboard, can be a piece of glass, can be a piece of plastic, okay? And I want to eliminate that for now, okay? Or a piece of plastic, okay? Can be wood too, right? That we insert in there. Okay, when we do that, something interesting happens inside this dielectric material that we inserted between the plates. Okay? What I want you to do, I want you to visualize that this dielectric that you see right in here is actually made of molecules, right? It's actually made of molecules. And here you go. I'm going to represent my molecules by those circles. That, by the way, is present throughout the whole material, okay? I want you to visualize that in this way. And right now, this capacitor is uncharged. See that? I didn't put any charges here. This capacitor is uncharged. Here are the molecules, okay? But when we charge the capacitor, an electric field is established between the two plates, okay? Between the two plates. And because we have those molecules that we saw there in the dielectric, something interesting is going to happen. This electric field is going to stretch the molecules. It's going to try to separate the negative charges from the positive charges. That's what we call polarization. The molecules is going to become polarized. Okay, initially the negative and positive charges were very close to each other. Okay, here you go. Initially, let me also put it right here at the bottom as well. Initially those molecules was round, right? And the negative and positive charges were very close to each other. Bring to front. Here you go. Bring to front. And this electric field is going to stretch those molecules. And by the way, if the electric field is strong enough, this electric field can even break the molecule apart from its charge. Okay? Can ionize the molecule if the field is strong enough. It's possible to do that. Okay, let's write that down in the notes. So you will leave it documented. Okay, here you go. All the equations that we derived last time on the capacitors relates only to capacitors having vacuum or air between their plates. Now the next question is the follow-up question is, what happens if we insert a different dielectric in between the plates? Okay. Okay, so the model predicts that the molecules in the dielectric will be stretched by the electric field of the capacitor. Will be stretched by the electric field. The electric field will try to rip the negative charge from the molecule, to rip apart the negative charge from the molecule. And and the molecule will become polarized. Okay? Polarized, forming what we call a electric dipole, right? When one negative charge is next to a positive charge, what we have an electric dipole. Okay. Here you go. That's, I want to copy this one and put that in the notes. I don't usually do that. I don't copy everything because those figures, those illustrations, they take lots of space in the final document. Okay. Sometimes this thing doesn't work. I don't know why. Let's try it again. Windows modified the snipping tool, and it looks like there's still some bugs in the new snipping tool that they came up with. So let's take a look again. Let's snipping tool. Let's try it again. Here you go. New. I'm gonna copy. Okay, now it worked. Huh? Capture. No, didn't capture. Oh my goodness. And not only didn't capture, but it quit as well. I don't think I'm doing anything wrong. Am I doing anything wrong? Here you go. Here you go. Here's the snipping tool, right? New. I'm gonna capture this guy. Okay, so here you go. Now let's highlight capture. Huh. Didn't do anything. Oh, what a shame. Okay, so I'm gonna do something else. That the software is misbehaving. Let's try. Instead of captured, I'm going to do something else. Okay, I'm going to copy. Copy only. Okay, now we should have a copy in the. Here you go, like that. Yeah, see? Center justify. Okay, so molecules of the dielectric material between the capacitor plates molecules become polarized. Okay. Now, the fact that we now have this polarization, something else happened within the capacitor. Okay, because we now have molecules inside the dielectric that are polarized, something interesting happens in the capacitor. Okay, notice that we have a distribution of charge, right? Here you go. We have a distribution of charge of the capacitor, positive and negative, but we also have a distribution of charges within the molecule. The positive molecule is facing the negative plate of the capacitor, and the negative side of the molecule is facing the positive plate of the capacitor. When something like that happens, what does it mean? What does it happen? When we have something like that, what does it happen, right? We create an electric field inside the molecule itself, an electric field that goes from the positive charge to the negative charge. Can you picture that? Electric fields always go from the positive to the negative. So let's see our illustration here. Here you go. Here you go. It's actually a smaller electric field, right? And this smaller electric field is represented by this light blue arrow from the left to the right, from the left to the right, from the left to the right. If we have this main field that points from the right to the left, and this tiny field that points from the left to the right, what happens? This tinier field is going to cancel some of the main electric fields lines that we have here. Are you following the idea? So instead of having all those 1, 2, 3, 4, 5, 6 electric field lines, we are going to have less. Let's say we're going to have 3 electric field lines. And these 3 electric field lines represent a weaker electric field. Okay? Here you go. Got? That's a very good qualitative way of understanding what happens in the dielectric at the microscopic level. It's a model, and it's a model that works very well. The net E field, here you go. The net E field inside the plate will be smaller because of the fields of the polarized molecules. Okay? So we can write that down there in the notes. Because now we have molecules inside the dielectric that are polarized, something interesting happens to the capacitor. Okay? The polarized molecules create their own electric field that partially cancel the main electric field of the capacitor plates. Okay? For this reason, the net field is weaker inside the capacitor, just by introducing this dielectric material. Okay? If we have vacuum in there, vacuum has no molecules whatsoever. Okay, so that there won't be any decrease in the main electric field. However, if you put air there between the plates, there will be a somewhat decrease in the main electric field, okay? But it's going to be tiny. It's going to be tiny. That's why I put vacuum / air. Air, as a dielectric, behaves in a rather similar way that vacuum behaves. Weaker inside the capacitor. Did you get the idea? So keep this idea in your mind, so you can see what happens at the level, at the microscopic level, okay? And now the new capacitance with the dielectric, now the new capacitance, no, not the new capacitance, the new electric field, is the dielectric, I'll call that E, is going to be less than the electric field, less than the original electric field without the dielectric. I'll call that E0. The electric field without the dielectric with vacuum between the plates is the E0, okay? Here you go. And so we can here write like that. We're gonna following this qualitative analysis, right? Following this qualitative analysis, we can state mathematically that the electric field becomes the electric field can be rewritten according to the following equation. New electric field is old electric field divided by a constant. Now let's say the constant of a material in which this constant is going to be greater than, oh, not this one, the other one. In which this constant kappa, right? The name of this letter is kappa. The Greek letter is the K, the Greek K letter. This constant is going to be greater than 1. And this constant depends on the properties of the dielectric material. Okay? So that's the first conclusion that we take, just by doing this qualitative analysis. Okay? So just by doing this qualitative analysis, we conclude that the E field between the plates of the capacitor decreases. Decreases when we insert a dielectric material. Okay? But recall, right? But also, recall that the capacitance of the capacitor is given by, remember what's the equation for the capacitance of a capacitor, of any capacitor, right? I'm gonna go back to the notation C for the, it's gonna be Q divided by V, right? That's Q divided by V. So now, this Q here that you see right in here is nothing but the charge in the metal plates of your capacitor. That's what this Q is all about. You can see that this, when you insert the dielectric, those charges don't change, okay? The moment that I insert this dielectric here, the charge doesn't jump out from the capacitor, nor additional charge jumping into the plate of the capacitor, okay? Notice that. I want you to think about that, okay? Looking carefully at the process of inserting the dielectric between the plates of the capacitor, we realize that the charge in the plates remain the same, okay? No charge jump into the plate or jumps out of the plate. The dielectric cannot do anything like that, right? The capacitor would lose its charge only if you connected a conductor an electric conductor between these plates. But if you're inserting a dielectric that doesn't let the charge move freely, this dielectric is not going to affect the net charge of the capacitor. In other words, the dielectric does not affect the charge, the original charge, okay, the original charge of the capacitor. Okay, so this guy here that you see right here remains the same. But what about the electric potential? But what about the electric potential? Right? The question is it going to be affected by the insertion of the dielectric material? That's what we must ask, okay? About the electric potential. Is it going to be affected by the insertion of the dielectric material, right? Okay, so let's examine. We do know that the dielectric material, dielectric material does affect the insertion, right? Insertion of the dielectric material does affect the electric field of the capacitor. We also know that there is a relationship between the electric field and the electric potential, okay? Between the plates of a capacitor. Remember that? There's a relationship for a parallel plate capacitor. For a parallel plate capacitor, the relationship is the following. Okay? The relationship is going to be E is V divided by the separation of the plates. Okay? So if the electric field was affected by the insertion of consequently, if the E field is affected by the insertion of the dielectric, then the electric potential must be affected as well. Okay? So now we're going to change our notation, okay? So let E naught and V naught be the electric field and potential of the capacitor before the insertion of any dielectric material between its plates. We are going to go, this one goes here, this one goes here, right? So we can say that before we insert any material whatsoever between the plates of the capacitor, the capacitance is going to be given by Q divided by V naught, right? Once we insert the dielectric material between the plates of the capacitor, we are going to end up having a new capacitance that's given by Q divided by V. Where this new V, okay? Don't forget this new V is going to be given by, here you go, this one that I want. Is going to be given by E times D. E times D. Like that. But let's not forget that my new E is going to be the original E without the dielectric divided by kappa. Make sense? Okay. Furthermore, let's not forget that the electric potential without the dielectric V naught is, V naught is also equal to electric, without, here you go, striking the wrong key, E naught times D, right? But E naught times D is exactly this term here in the numerator of the ratio, right? Consequently, the new electric potential will also decrease once we insert the dielectric material between the plates of the capacitor, okay? And now we are coming to a point that we can figure out what's going to happen to the capacitors. What's going to happen to the capacitors? Okay. So going back to this equation here, right? Note that we're going to substitute V right in here. My V goes here inside, right? We go. The K, kappa, right? Not the K, the kappa can be placed at the numerator, right? You go. And let's not forget that the capacitance, the original capacitance without the dielectric, just with vacuum between the two plates, is Q over V naught. And look what happens to the new capacitance when we insert the dielectric. When we insert the dielectric, the new capacitance becomes greater than the previous capacitance. Okay? So, in conclusion, when we insert a dielectric between the plates, comma, the electric field decreases, the electric potential decreases. Consequently, the electric potential energy must also decrease, okay? Electric potential energy of the capacitor must also decrease, okay? Comma, but the capacitance increases, okay? In conclusion, when we insert a dielectric between the plates, the following happens, right? The following happens. happen? One, the electric field decreases. Two, the electric potential decreases because the electric potential decreases, comma, the electric potential energy that the capacitor carries must decrease as well, must also decrease, right? But the capacitance increases. The capacitance increases because it is inversely proportional to the electric potential. Okay, we usually say that the internal energy of the capacitor decreases when we insert the dielectric between its plates. So you can do less work, right? In other words, we can do less work with this capacitor, less useful work with this capacitor. Okay. Now let's take a look at this kappa. Let's take a look at this kappa, okay? This kappa has different values for different dielectrics. And let's take a look at the book, right? Wiley. Let's see here. Yeah, we got it. We're going to logging. Where's that? Logging. Physics 7. Wiley course resources. Let's take a look at the value of kappa for different dielectric materials. This is documented in the literature. We can measure kappa. Capacitors and dielectrics. Here you go. Okay, and we can even measure the electric potential using a multimeter, okay? Remember the multimeter that we used before in the lab one? You can have the two plates, there is air there inside, and then you insert a dielectric. Well, you have air. Initially, you have air, right? The two plates of the capacitor. And the capacitor looks exactly like that. Two metal plates parallel to each other that you apply a potential difference with a battery and you charge them. And you put a multimeter between those two plates, connected to those two plates, before you insert the dielectric, and you measure an electric potential difference. When you insert the dielectric, the electric potential difference also decreases. That happens in real life. This is not some far out theory that doesn't explain the world, right? This theory, it explains the world very well. And that's what he's illustrating right in here. We're not going to worry about random access memory. You can skip that. This random access memory is something so you see that we have a transistor here. Transistor is a device that we cover in a more advanced course, the dielectric constant. That's what I want to show you, the dielectric constant. Okay, here you go. The same illustration that I got, right? Vacuum between the plates, a dielectric between the plates. The molecules become polarized. The electric field of the polarized molecules decrease the net field, right? And here you go. We have this kappa. We call it, this is a dielectric constant. We call it a dielectric constant. Reduction in the electric field is described by the dielectric constant kappa. And what I want to show you, let's see, what's the, okay, here you go. Here are the constants for the, here are the numeric values for the dielectric constants, okay? Dielectric constant of the vacuum is 1. Dielectric constant of the air is very close to 1. See that? I told you. The dielectric constant of the air is very close there to the air, and the difference is small. It's so small that we can say that the air behaves like the vacuum. Okay? The air, the electrical properties of the air, the dielectric properties of the air is very similar to the dielectric properties of the vacuum. If we insert Teflon, Teflon is that little coating that goes at the bottom of your frying pan, right? It's a plastic coating that was discovered by someone, DuPont, right? DuPont or 3M, let's see. Let's say who invented Teflon? Teflon, I believe it's just DuPont, right? Who invented? It was either DuPont or 3M. Let's see here. Roy Plunkett, DuPont, yeah, the guy at DuPont. It was an accidental discovery. Okay, just an accidental discovery. Benzene, paper, regular paper. Royal, oh, not a regular paper, but the royal gray paper, right? 3.3. Mica, have you heard of mica? Ruby mica. Let's see if you have a picture of mica. It's some small flakes. Many stones, they have some small flakes over their surface. It looks like a glassy material. Ruby mica. When I was growing up, I used to look at those stones out there, and I would see that. Let's see if we have a picture of mica. Oh, ruby mica is reddish, okay? But mica, no, mica is transparent. Okay, it's a very good dielectric material. Oh, it's a good electrical insulator. Very good dielectric material, very good electrical insulator. Let's see if we have a picture of mica here. Mica. Yeah, okay. Mica for isolated mountain. See, that's how it looks like. And those things, they occur in the surface of several different minerals, several stones. Let's see if we have a picture of a stone with some flakes of mica. Oh, embedded. He's talking about embedded. Let's play this one a little bit. Yeah, here you go. Yeah, that's how it looks like. This one is embedded, but it can also occur at the surface of the stone. Okay. Mica, let's go back to our book. Neoprene rubber, 6.7. Methyl alcohol, 33.6. Water. Water is a dielectric material. Is a very high dielectric constant. Okay. Very high dielectric constant. Can you remember? You don't have to memorize the dielectric constant of everyone here, but at least the dielectric constant of those two, okay? The dielectric constant of air, you can say that's equal to 1. The difference is so small, it's less than 0.1%. We can even, let's see. Here is 1%, this decimal place is 1%. Here is 0.1%. Here is 0.5%. Okay? It's less than 0.1%. It's 0.05%. The difference is so small compared to vacuum that we say that the dielectric constant of air is 1. Any questions? Let's see here. Constant charge. Oh, here you go. Capacitors are used in keyboards, okay? Each key is mounted on one end of a plunger and the other end is attached to a movable metal plate. Figure 1919. Let's see. Here you go. See that? Here's the dielectric. Here's the metal plate of the capacitor. Here's the other metal plate. Here's a plunger. The moment you strike the key, the distance between the plates of the capacitor change. Can you picture that? In one kind of computer keyboard, each key, when pressed, changes the separation between the plates. Okay? And now, because you're changing the separation between the plates, the voltage between the plates changes as well. Okay? The voltage between, and so if you have a multimeter monitoring each of those capacitors, the computer will know which key was struck, has been stricken. Okay? Which key has been stricken. That's how we come up with the computer keyboard. Energy storage in a capacitor. Let's cover that. Let's see. We need to cover that as well. Yeah, okay. That's the only thing we need to cover. We have this is already, let's see, 10:30, right? Let's try to cover that quickly so you can finish this chapter for the exam. Okay. Now we're going to calculate the potential energy that a capacitor carries. Say that in the, and let's see, before you see if I can, no, I can't. I want to copy that table of the dielectric constants here into my notes. Here we go. You don't need to memorize the whole table, but you have at least to memorize that the dielectric constant of the vacuum and the air, that are almost the same and equal to 1. Now, dielectric constants for different dielectric materials, right? For some common dielectric materials, for some common substances. Now, let us calculate the potential energy that a capacitor with vacuum between the plates can store, right? And this potential energy is the same potential energy. It's not the same. I wouldn't say exactly the same potential energy. Is energy that can be used to do some useful work. Okay. By the same token that if you raise a mass against the force of gravity, you add potential energy to the mass. When you charge a capacitor, you also add energy to this device that can be used for useful type of work, right? Now let us calculate the potential energy that a capacitor with vacuum between the plates. Let us find out that a capacitor can store. That a capacitor can store. Assume the volume between the plates with the vacuum. The volume is filled with vacuum. Okay? Then we worry about the energy once we insert a dielectric. How do you find out, right? How do you calculate that? Okay, we go back to the definition of electric potential. Okay, the difference of electric potential is equal to the difference in electric potential energy divided by the charge. Okay, that and then we can here write. Don't forget, we want to calculate that here. That's what we want to calculate. And in order to calculate that, we have to isolate one from the other. All right, here we go. Delta V times Q. I'm gonna put Q in front. I don't want it bold-faced. I copy and paste. Okay. In the next step, we are going to get the equation for the capacitance. Okay. That's the equation for the capacitance. Since we have vacuum between the plates, kappa is going to be equal to 1, right? And let's not forget, I want to use the same notation that I have here. Delta Q. And don't forget, is the magnitude, right? Is the magnitude. Both of them is the magnitude here. Once we finish that, we can, interesting. Gotta do one by one. What a waste of time. Could have done both in a single stroke, right? But no. Right here. And now I solve for the electric potential difference in terms of the charge and in terms of the capacitance. Okay. And that's what we get. We go like that. Substitute that right in here to see how simple it is. It's not of substitute right in here. Delta V. I'm gonna just repeat it. Okay. When we multiply the Q and its magnitude, we get exactly Q squared, whether Q is negative or positive, doesn't matter, right? That's what we get for the electric potential energy of a capacitor. But this is not quite the correct result, okay, folks? There's something missing there in the derivation. Okay, and what you have to understand is that we have a linear relation between one and the other. Okay, the actual correct result is going to be half of this value here, half of Q squared over C. I'm not going to struggle with that, but just remember, okay, this is not the correct derivation, but kind of reaches a similar result. That depends only on the half, okay? The correct result is half of what you see right in there. Okay, here you go. Here you go. You can, I'm gonna put it here. Which can be here written in 3 different ways. It can be here written in terms of Q squared over C. Then we can substitute C in terms of its own definition, and we get half QV, Q delta V. And there is one more way of rewriting it. Okay. Q delta V. And how do you do that? You just write down Q. Let's see here. Let me do this step by step. So you have everything in, here you go. Yeah, here you go. Here you go. Here's the equation, right? C is Q over delta V. So you get something like that. And then you can here write that's what you got, right? And then you can get the same equation here and substitute for delta V. Let's get, that's what you want here. Here you go. C. And when we do that, you get this third result, Q over C. And Q over C is, no, we go back to the original, right? Q delta V, let's see here. No, we want, okay, what we want to, here write Q in terms of the order. Here you go, C, now we got it, delta V. When we do that, we get a third format of the same equation, like that, right? And substitute that right in here, C delta V squared. Three different ways of expressing the potential energy of a parallel plate capacitor. Okay, and let's see here. That's the first. Let's see, here you go. That's the first one. That's the second one. No, that's the second one. And that's the third one. And that's the third one. In terms of Q and C, in terms of Q and delta V, in terms of C and delta V. Three different ways. Three different equations, okay? And let's see if we all we need, if you have anything else here. Yeah, we can write down the energy of a parallel plate capacitor. Let's see how it looks like, right? Energy stored by a parallel plate capacitor. See, 1, 2, 3, right? He's using V instead of delta V. Lowercase q instead of uppercase q, right? Like I used. Energy is stored by a parallel plate capacitor. Parallel plate capacitor. Let's see which one I'm going to use. Let's use this one. Okay. First, parallel plate capacitor with vacuum between its plates, right? With vacuum between its plates. So here you go. Vacuum between its plates. I'm gonna put that notation U naught and C naught. Q doesn't change, right? Q doesn't change. We do know, we derived previously that C naught is what? Is the area of the parallel plate capacitor times epsilon naught divided by D, the separation between the plates. divided by D, the separation between the plates. So D goes upstairs. Okay. And that's what we get for the parallel plate capacitor. But there's more. There's more we can do. That's a delta U naught, right? What if we, not a parallel plate capacitor now. Now what is going to be the energy stored by a parallel plate capacitor with a dielectric between its plates, right? With a dielectric between. Now it's not going to be U naught, right? I reserve U naught for the parallel plate capacitor, energy of parallel plate capacitor that has no dielectric between. And here is the parallel plate, is the capacitance with no dielectric material, but just vacuum or air. Okay, recall that the capacitance increases, right? The capacitance increase, what is going to be kappa times C naught. And delta U in this specific case is going to be delta U naught. What happened here? Delta U naught. Oh, gosh. Delta U naught. Oh, you don't. Oh, I see. Okay. I erased instead of copying it. Delta U naught divided by kappa. Oh, right? You decrease the amount of energy, electric potential energy. Did I write that down there upstairs? Let's see here. That energy, but the capacity, because electric potential, the electric potential. Okay, yeah, I did write that down here. Must also decrease, right? By a factor kappa. Now we're going to do something else. Let us calculate the energy density or energy per unit of volume of the capacitor. Okay, so here you go. We want something like that. We want the energy per unit of volume, the energy density or energy per unit of volume is going to be, I'm going to put lowercase v for the volume, okay? And the volume can be also the area of the capacitor, right? If it's a parallel plate, it's going to be area times the distance, right? Going back here, that's the area, the volume between the plates is going to be the area of those plates times the distance. Okay, and I will it's going to be, let's see here, delta U is going to be delta U over kappa, delta U naught over kappa. Delta U naught we calculated before. Let's bring kappa to the bottom. Okay. Delta U naught is, we calculate delta U naught is this one here. Let's write it down. Delta U naught is this value here. So I will place right here at the top. The D, let's see here if I did something incorrectly. You know, let's see here. Let's do it a different way. This one's going to become too complicated. I'm going to do it in a different way. Let's see, D cancels. Yeah, let's do it in a different way. Okay, we found that the potential energy is half CV squared, right? This one is easy to memorize, right? It's easy to memorize because it's very similar to the equation of kinetic energy, right? Half mass velocity square, right? It's just let's calculate the electric potential energy of a parallel plate capacitor using this equation instead of what I'm doing here. And then I'll worry about the energy per unit of volume. Okay, so let's go next step. Capacitance is given by this ratio here. This ratio, that's a parallel plate capacitor, right? Area over distance between plates. And we have delta V. And then what else can we do? We can replace the delta V by the equation of the electric field. Okay, let me take out this delta V here. The equation that involves the electric field is E times D. E times the separation between the plates. Okay, we expand this equation, E squared, D squared. Here you go. Now we can do some simplifications. D squared canceled with D. And now I want you to pay attention here to this term, right? A. Let me keep this one here. And let's go to the next step. I'm just going to commute this A with the other parameters. I'm going to put it next to D. Why am I doing that? Because A times D is my volume. See that? Okay. And I'm going to put V here, lowercase v for volume. And then we end up with the simple equation delta U over V is half kappa epsilon naught E squared. Right? And delta U over V, we call lowercase u for energy density. Energy density is directly proportional to the square of the electric field. The higher the electric field, the more energy you can store in the capacitor. And we can now complete the list of material for the first exam. Right in here, right in here. Okay. Right in here. We covered everything. Let's see, someone's trying to come in. And it is 11:53 right now. No, 10:53 right now. Let's have our break. break 10:54, right? Let's AM to, let's see, 11, 11:09 AM. Any questions? Okay, so let's see. There are some messenger. I have a question for the exam next week. Yeah, what's the question, Susan?
Hi, Professor. So I seen that the time is from 8 till 10.
Did I put 8:50 there? I put
Yeah,
8:50,
8:50.
right?
Yeah,
Yeah, okay,
8:50
let me
to
correct. Thank you
um
for pointing that out. Let me just fix it first.
okay.
8:50 used to be the time that we used to meet for this class, and then they changed it to 9:40. Thank you for pointing that out. Let's see, where's my syllabus? 8:50. Yeah, okay, 9:40.
Oh,
Wow.
thank God.
I didn't notice that.
Okay.
9:40 is going to be 11:40. 11:40. Let me just fix it. And look at the final exam schedule, right? It's 9:10. Yeah, any other question?
No, that was everything. Thank you so
Okay,
much.
thank you for picking that up. And I will see you in 15 minutes. Okay, till then, bye-bye.
Bye-bye.
I'm back here. And okay, so we finished with the material for the book, for the exam, not for the book, for the exam. Okay, and 18 and 19. And now let's continue with lab one, right? Lab number one. We didn't finish lab number one. That is, that's something that I haven't told you before. I didn't have time to tell you. But let's get the let's first see if everybody's here, right? Let me let's see roster. Okay, so today is March 4th. Let's see, Mario Showa. Are you there, Mario? Okay, I gotta do something about Ahmad. Are you there? No. Tatiana. I don't see Tatiana. And Delisha. Delisha's not here, right? Oni, are you there? Oni?
Yes, I'm here.
All right, thank you.
You're welcome.
Mirage. Mirage, are you there? Yeah, I don't see Mirage here. Susan?
I'm here.
Okay. Evelyn Ayala?
I'm here.
Okay. Group 3, Cristina Balderas? I don't see Cristina. Queen Castaneda?
Here.
Thank you. Emily Serna? I don't see Emily. Isabella Cisnero. Isabella. I don't see Isabella either. Next, Gabriela. Gabriela Edwards. Let's see, Gabriela here. No, I don't see Gabriela. Princess.
I'm here.
Thank you, Princess. Kimberly Morales.
Here.
Okay. Trin Hernandez. Okay, thank you, Trin. Stefan. Stefan Steven. No, I don't see Stefan, right? Jeremy Landes.
I'm here, Professor. Stefan, I'm here.
Oh, Stefan is here. Okay. Okay, Stefan. Good. Thank you, Stefan. Paola Leones. Thank you, Paola. Pedro Josué Lopes. Pedro. I don't see Pedro, right? Next, Isabel Medina.
Here.
Thank you. Ariane Navidias. I don't
Here,
see-
Professor.
Oh, you're there? Okay. Next, Arwa.
I'm here.
Okay, so who doesn't have a group, by the way? Does everybody has a group? If you don't have, let me know. Okay. And Catherine Perez. I don't see Catherine. Nadia Prum.
Here.
Thank you. Jason Cervellon.
Here.
Okay. And Dana Terry.
Here.
Thank you. Ramon Moran. Ramon, I don't see Ramon. Audrey.
Here.
Thank you. Next, Carlo Gallardo. Okay, I see Carlo in the roster, but I can't hear from Carlo. And next is Steve Sanchez. Okay, I see Steve here in my list. Ben Bendoy. Thank you, Ben. Next is Noemi Martinez. Oh, I don't see Noemi. Luis Cruz. Hello, Luis, can you hear me? Okay, let me put a star here under Luis' name. Jenny Maldonado.
I'm here.
Thank you. Mikara Alkema. I don't see Mikara. Next is Ryan. I don't see Ryan. Chris Anthony. Oh, I don't see Chris either. And Juan Torres Arellano. Okay, thank you. And how many students we have here? 23, right? Yeah, okay. The numbers match. We are in good shape here. And okay. Let me see. Luis Cruz. Okay, thank you, Luis. Luis Cruz. Let's see, Luis. It's right in here. Take a look. Good. So let's take a look at the spreadsheet. Lab here, raw data, lab 1, copy of data. Okay, let's get this one here. It's looking at. Okay, at this point in time, you must already have your first graph, right? Let's get the notes for the first lab here. Lab. Noemi. I'm sharing the screen, right? At this point in time, you must have your equipotential curves, okay? At this point in time, you must have equipotential for 2 volts, equipotential for 4 volts, and so on, right? Let's see if I plot everything at once. Let's see, insert. Yeah, I got it. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. What's going on here? Let me see. There's something wrong here. Let me try it again. 1, 2, 4, 6. That's just another way of plotting the. No, it didn't work, huh? No, it didn't work. Okay, so let's for some reason it didn't work. Okay, so let's here you go. That's the first equipotential. I want to add one more equipotential. I have to select the data, add add 4 volts, highlight. Let's see here. Yeah, I gotta take this graph outside the. Okay, here you go. When you plot, make sure that your graph is outside the table. Otherwise, you won't be able to select the proper columns, right? Here goes. Select, right click, select data. Okay, you're going to add one more equipotential. That's going to be 4 volts. Highlight the X. The X values. You erase what you have here in the Y values. They put some junk in there, Highlight the Y values. Click OK. Click OK. You have your second equipotential here, right? Left click again. Let's see. So I'm also here. Who is that? Steve Sanchez. Okay, let me get here, Steve. Steve Sanchez. Okay, good. One more student. Let's see the other they didn't answer. Carlo Gallardo, are you there? Are you there? Carlo Gallardo. Yeah, okay, good. And now Noemi just joined us, right, Noemi? Just let me know you're there. I'm not hearing from Noemi. Okay, so let's continue. Okay, so here you go. Third equipotential, click, right? One of the data points, right click it, select data, add, and then you gotta write down 6 volts here. Select the X values for the 6 volt equipotential. Erase this number 1 that you have here in the series Y values. Highlight the values for Y, right? Click OK. Don't forget. Oh, by the way, you can also edit this series 1, and instead of series 1, just put 2 volts, right? Yeah, now you have 2 volts there. We're going to add one more for 8 volts. 8 volts, X value. Highlight Y value. Everything that we did last time, right? One more. I gotta click OK here. Let's click OK here. Okay, 2, 4, 6, 8. And the last one is going to be 9. Left click, right click, select data, add 9 volts, X value, Y value. And then we have the equipotent. Oh, wait a minute, something there. Okay, gotta erase it first. Y value again. Now we should have all the 9 equipotentials. Make sure you make a nice graph, right? What you have here are the equipotentials of 2 parallel plate capacitors, okay? And we have those equipotentials, they're almost evenly spaced, and you are going to see it when we plot the second graph. They are almost evenly spaced. And what's going to be the second graph? The second graph is going to be this one right here, X average and V average. It's going to be V average in the Y axis and the X average along the X axis, okay? What are we plotting here exactly? Just take a look at this cell that we have here. Let me zoom in a little bit more, okay? This cell, each of those cells along the V average is taking the average values of the voltage. Okay, 1, 2, 3, 4, 5, 6 different values of the voltage that we measure with our multimeter, and it's taking the average value of those 6 volts. This other one is similar, taking the average values of those 4 volts. They are not exactly 4 volts, okay? They're slightly off as 4 volts. One is 4.008, the other is 4.041. Okay, it's in real life, it's not possible to get exactly 4 volts. Okay, but you can get close enough. And then we have here, in this case, 4.04 volts is just 1% off of what you're trying to get, which is exactly 4 volts. That's why I'm taking the average. Okay, the same thing for 6 volts and so on. What about the X average? The X average are going to be the average of those values that you see here. Okay? The average value of those values and so on. And that's what you're going to plot next. When you plot it, you get exactly what I mentioned to you during the lecture. You're going to get a linear relationship between the voltage and the X position. Okay, and here you go. I'm going to insert it. Chart. Yeah, see that? It's a linear relationship. It's a linear relationship because the electric field is uniform throughout this space. Okay, and once you get the slope of this equation, you can state the value. You can say what is the value of the electric field. Okay, so plot this graph now. And I'm gonna get the notes of our previous lab meeting. Lab 1. Let's see here. Okay, lab 1. No, not this one. I want the other one. This one right here. Lab 1. Yeah, I'm gonna just copy and paste what we did last time. So I know where we stopped, right? Nope, stop right here. And then continuation, right? Last time we stopped right here. We finished plotting the equipotentials, which was our first graph. from those equipotential lines. Draw the electric field normal to these equipotential lines, okay? That's our first graph. That is our first graph for this lab. I'm going to highlight it. Stop here in the first lab meeting. Stop it here in the first lab meeting. Pick it up and pick it up in the next one. Go. Figure, highlight it. This is our first graph for this lab. Okay. Next. Okay, I'm gonna go start. Here you go. Like that. Next. Plot the average versus X average. That's table number. Table number 1-2. No, 1-2. Yeah, table 1-2. Table 1-2. Okay. Notice that you have a linear relationship between V and X, which is the expected relation for a uniform E field, right? And I'm going to 1, 2, 3. I want the subscript. One subscript here. I want subscript here as well. And to make it look nice, just italicize V, italicize X. Just italicize X. Okay, going back to my spreadsheet. Here you go. So we should all, you all should get a straight line. And then what else do you do? Click one of the data points, right click, and now you're going to add the trend line, right? Just like we did in Physics 6. If you're taking my lab for the first time, I'm gonna go a little bit slower. Add trend line. Again, right? Click one of the data points, right click it, add trend line. Okay? And now you see that a straight line is plotted here. That's because by default, Excel assumes that you want to plot, to find a linear equation that fits all those data points, 1, 2, 3, 4, 5. And what else do you do? When you right click and add trend line, this pane shows up here on the right side, okay? And what are you going to do? You're going to display the equation on chart. You're going to display R-square value on chart. R-square value is a statistics parameter that's very important. The very important statistic parameter, okay? It tells you how close this straight line, this regression equation is to your data points. Okay? So let's, I'm gonna write it down in my notes that you have a linear relationship between V and X. Click one of the data points, right? Right click it. All data points should be highlighted. Should be highlighted. Right click one of the data points. Select select What's that? Add trend line. Select add trend line. Right click one of the data points. A drop down menu should show up. It should. I'm gonna organize in a different way, like that. Click one of the data points. Should highlight. Should highlight. Point. Right click one of the data points. 3. All data points should be highlighted. Oh, no. Sorry. Click on the data points, right click on the data points. A drop down menu should show up. A drop down menu should show up. Select, add trend line. Trend line. Okay. A pane on the right side should appear. 5. Select check. What do we have to do? We have to check. Yeah, check display equation chart. Display R-square value on chart. Check display equation on chart and display R-square on chart. Right? Like that. And now we have here the equation that fits as closely as possible the data points that you have. It's 55.598 minus 0.0995, okay? And what is important about this equation? What's important about this equation is this slope value that you see right in here. This slope value is exactly the electric field value. Okay, the value of the electric field, volts per meter. Volts per meter, yeah, volts per meter. Okay, that's what this thing is all about. It's all about, okay? So from this simple experiment, we were able to determine the value of the electric field distribution, but just the intensity. Is that clear? Okay. So let's see here, going back here to the notes, right? Because this charge distribution is that of a uniform electric field, comma, the slope of the equation that you obtained represents the intensity, the magnitude. Let's put here the magnitude of the electric field of this configuration. Right? And this electric field points from the positive charge to the negative charge. Points from the positive charge to the negative charge. Okay, the negative charges are right in here at the equipotential equal to 0. The positive charges are somewhere around here at the equipotential of 10 volts. Okay. So the electric field points from the right to the left, from the positive charges to the negative, towards the negative charges. Make sure like I said before, change here the format of those numbers in the graph, right? You don't want to have a scientific format here along the x and y axis because it's difficult to read. Okay, you don't want, so how do? You double click here, right? And click, let's see, numbers. See here, scientific format. No, highlight number, numeric format, and put 2 decimal places. 2 decimal places. Let's see if we, well, why didn't show 2 decimal places there? That's so strange. Number. Oh yeah, now it showed up. Okay, now it showed up 2 decimal places. It's easier to read, right? And you want to increase the size of this font as well. Let's see if we can do that. Font, yeah. Click it, right click it, font. I want to increase to 14. Let's see, 14 is a good size. Yeah, so 14 is a good size. Exposition from 0 to 0.2 meters, not centimeters, but let's say from 0 to 20 centimeters, right? You do the same right in here. Click, right click. Now let's see, double click. You gotta double click it. Go here in the axis options. Axis option. You want, let's see here, number. You want number. And then instead of scientific, you select number, 2 decimal places. Right? We have 2 decimal places now. And let's see if we can change the font here. Doesn't look like we can change the font here. So you gotta go outside, unclick the graph, click it again, right click and font. 14, right in here, 14 size, 14 font size. We did that before, right? I walk you through. I don't like to display the chart title. But don't forget, you have to include the axis title. Let's do that again. We did that last time. Let's do that again. Are you folks following? Am I going too fast?
No.
No.
Okay. Most of you did that before, right? Hopefully. Okay, so when you click the graph, watch what happens here at the top, right? When you click the graph, all those 2 options shows up. Chart design and format. You want to click chart design and go to add chart element. Okay. And let's not forget, okay, if your computer is different, you can and those instructions doesn't show up in your own computer because Macs sometimes displays stuff differently. You can always consult the help here at the top, right? So here you go, add chart element, arrow down, axis title, primary horizontal. Okay, we're going to write down something here, and then you're going to do primary vertical. Yeah. Okay. I want in the primary horizontal, I want you to type X between parentheses, the unit in meters. Notice that the font is small, right? I want a larger font, okay? Put a font that's larger than the other one. The other one was what, 14? No, yeah, just 14, the other one, right? Let's make this one 16. Let's put 18 instead. Let's put 18. And I like to make it bold-faced as well. To make it look nice, let's italicize the meter. Let's italicize the X, right? Let's see, which size is this one here? This one, I forgot what size we used. Was that 14 or 16? I put 14, okay. This one is 18, right? And you do the same here. 18. Bold face. And then you type Y between parentheses, meter. And then you erase everything. Okay, that how, and again, italicize those letters to make it look nice. Okay, that's the trouble we go through when we are publishing something. I do all of that in my reports when I get money from the government, and then I have to tell them, show them that I did all the work. I plot all my graphs and go through this whole problem, the whole trouble. I have done that so many times I think it is even fun to do that. The more you do it, the more you like. The more you like it, the more you take a taste. You develop a taste for it, right? The more you do, the more you develop a taste for it. At the beginning, sounds like too much work, frustrating work. But eventually, when you get the hang of it, you start to like plotting this stuff. That's our first graph. Our second graph is this one here. You do exactly the same thing that we did, right? Let me increase the size. X-axis. See that those values are all 2 decimal places, right? If we put, change the format of this axis, when you click it, this pane shows up on the right side. You want to click the bar chart, and then the number, and change the category from scientific to number, just like the other. But see, because we have 0 decimal places, all you end up having here is number zeros, right? So just increase the number of decimal places. Let's see if it's 2 decimal places enough. Yeah, 2 decimal places enough. 0, 0.02, 0.04, blah, 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 right? And here we're going to do the same. Double click, scientific to number. Do we need 2 decimal places? Yeah, let's put 2 decimal places. Well, now let's put for this one, you can put just 1 decimal places. We don't even, can even have 0 decimal place for this case here. And then you have to increase the font size, right? This time, let's make it 16. Let's make the font 16 here. Yeah, 16 in the vertical, 16 in the horizontal. 16 in the horizontal. Click OK. And to make it also this equation look, to make it easier to read, let's increase the font size of this one too, right? Let's see if I can do that. Yeah, I highlighted, right? I highlighted here, right click it and font. I am going to put it 14 in this case. I don't want it larger than the axis. It didn't increase in size. Why is that? Let me try something else. 14. What about now? Okay, now increased. Arrow. Okay. Make it easier for us to read everything that's here. See that this number R is square, right? It's very close to 1. Okay, this number here has a name. If you took the course with me, you already know the name of this parameter. It's a statistical parameter. It's called the determination coefficient. Okay, the determination coefficient, R square. Let's see, R square. Okay, the R square value is called the R square value is called the determination coefficient. Just R, the R value, not the R square value, but the R value is called the correlation coefficient. This value is very important, okay? R square can take any values between 0 and 1. Okay? You can take any values between 0 and 1. Whereas the R value can take any value between -1 and 1. Okay? I can put like in mathematical format, right? Take any value between, I'm gonna put it here, 2 superscript 0 and 1. It should be greater or equal, less or equal, okay? Whereas the correlation coefficient is going to be between -1 and 1. So we got to do more. We got to do more, right? We got to put the title of the axis. Click the graph, chart design. If I unclick it, notice that if I unclick the graph, the chart design and the other one there disappear, right? So you have to click the chart for it to appear. Chart design, add chart element. Axis title, primary horizontal, primary vertical, just like before. And we are going to use font size 18. 18, right in here. Here you go. Here you go. And we do the same here. Right click, font size 18. Okay. Oops. You don't want one superimposing with the other, otherwise it's going to be difficult to see it, right? So what do? You shrink a little bit the graph, okay? You shrink a little bit the graph. There's one more thing that I have to do that I didn't do it yet. Here you go. I gotta right here, the axis title is going to be VAVG. Like that. Low font, subscript, here you go. I want to italicize my V, and I have to do one more thing. I have to put the unit of V average, okay? Make sure you get out of the subscript. Yeah, here you go. So, but that's okay. I'll fix it. Okay, before making it subscript, make sure you type on the side between parentheses V, right? The volt, which is the unit of voltage. And now I subscript the AVG. Now I subscript the AVG. Font, subscript, click OK, VAVG. If here is VAVG, in the other one is going to be XAVG. XAVG, huh? Here you go. And the unit for XAVG, AVG for average, is going to be the meter. Let's not forget, you gotta boldface it. Boldface to make it look nice. And I didn't boldface it. Boldface, yeah, it did. Yeah, it did boldface, but didn't italicize, right? So you gotta do the italics again. And it's gonna happen here the same thing. When I do the boldface, the italic is going to disappear. Font, let's see if it disappeared. Font, bold. Yeah, it disappeared, right? So you gotta do the italic all over again. Here you go. There is one more thing that you have to do. There is one more thing that you have to do to make to give a final touch to this graph of yours. Okay? I usually like to think that those graphs here that we're doing is like a masterpiece, right? We're painting a masterpiece with the computer. So make sure it looks good. So what's missing? Notice that we have a big blank space here, right? We have a big blank space here. We have a big blank area here as well. Make sure you optimize this area so you don't have those big blank areas there. I will correct your graph according to that. So how do we do that? We have to adjust the axis. You double click on the x-axis and instead of starting at 0, you start. Let's see where we're going to start. Sometimes it's just a little bit of a trial and error, okay? I think I'm going to start at 0.03. Let's see if 0.03 is a good one. Yeah, it looks good, right? Maybe, let's see. Let's see. Yeah, I want the other one to go to 0.17, maybe. Let's see. Let's see where this one's finished. This one's finishing 0.2. Yeah, it looks like it's why 0.2? There's something wrong here. It can't be 0.2 because we have 0.18 here. Let's take a look where in the table, what's the number we have right in here? Yeah, it's not showing.
I think I saw something just now when you hover over it, it said 0.16.
Yeah, 0.16. Let me see.
I think so.
Yeah, I know it doesn't show 0.16. Say, 0.16. But we have between parentheses 2 exponent. Must be 0.16, right? But it has to be 0.16 because this one is 0.18. It has to be 0.16.
Right.
Yeah. So yeah. But what are those other numbers in parentheses, right? I do not know what those other numbers in parentheses are. Strange. The 9 certainly is the voltage, but what about this 2 times 10 to minus 1? It must be, you know what? Yeah, I know what it is. It must be 0.16, but because of the format, he it doesn't have enough decimal places there. He's displaying as 2 times 10 to minus 1. That's why. Yeah, that's the reason. That's the reason. Okay, so let's go ahead and, let's go all the way down to 0.17. All the way up, right? Not all the way down, all the way up. And now our graph is starting to look good. And one more thing that I want you to do, right now the spacing between numbers is 0.05, right? That's the 0.05 I'm talking about. Put it 0.02. Here you go. Put 0.02. We gotta do in the vertical axis as well. Let's see, where would I start? I would start at 1. Okay, I will start at 1. Yeah. And I think that's the most we can do for this graph. We still have a little bit of space here, but we are not going to eliminate the space, because if I eliminate the space, this data point is going to be too close to the x-axis, okay? There is also a little bit of space here, but I'm not going to eliminate the space because this data point is at 9 volts. It's going to be too close to the axis if I eliminate the space. Okay, 2 graphs. Let's see how you're doing. I want to know if you plot the 2 graphs. I'm going to call you one by one. And again, if you don't have a group member, let me know. Okay, and here you go. This one is going to be right in here. I'll get this one and put it here. Right, I'm going to put some blank columns here. the first thing I want to know is that did you plot graphs? Did you plot the two graphs, right? Let's start with Oni. Did you plot the two graphs, Oni?
Yes, me and my group did.
Okay.
Yeah.
Okay, and do you have any questions? Do you have any problems plotting the graphs, or you're good?
No, we're good.
Okay, good.
There's a question I have to ask you though, but it doesn't have to do with the graph or anything.
Okay.
It just has to do with the time for the exam. So since you changed it like a few minutes ago, like an hour ago or so, can you change it on Canvas on the modules to make it official so that I can have a copy for myself?
Yeah.
Yeah, because the thing is, I printed it out and then I thought that was gonna be the schedule for the exam, but I just had to, yeah.
Okay. Yeah, I will. I'm going to do that when I have the exam ready. Okay. Maybe I can do this before having the exam ready. I'll look into that. I'll look into that. Okay.
Okay, to change the times, right?
Yeah, to change the time. Yeah, I can do that. Yeah, I think I can do that before writing
Excuse
down
me,
the.
Professor.
Okay, thank you.
Okay.
I have a
Okay.
question.
Yeah.
So I'm in a group 10 with Arwa. My name is Aryan. Group 10. She's telling me that the last class you changed her group to someone else. It's
Yeah.
called Gabriela Edwards.
Yeah, that's right.
She want,
She moved to
but
another
it's
group.
still, yeah, it says
Yeah,
still in the same. I want to see who is my teammates. That's my question.
yeah, that's right. Let me check here. Ara moved to the group of Gabriela, right? Ara?
Yeah.
Let me see. Gabriela. Okay, now she's group number 5. So let me update it here. And Isabella, is Isabella here? No, I don't see Isabella. Gabriela, are you there? Gabriela is not here either. Okay. Who doesn't have a group? Let's see. Who doesn't have a group would like to join Aryan, right? Your name, right?
Yeah. Yeah.
Let's see. Well, I'll try to find someone to join you. Okay, Aryan. At this point, we don't have all students here. Okay, and I'll try to find another partner to work with you. Okay.
No worries.
In this meantime, just work on your own for now, and then
Sure. Thank you.
I'll try to find you a partner to work with you. Good. Mirage is not here, right? Okay, so Susan, are you there?
Yes, I'm here.
Okay, do you plot all the two graphs, Susan?
Yes, I have.
Okay, no problems with plotting the graphs?
No problems, no.
Okay, thank you. Next is going to be Evelyn.
I'm here.
Do you manage to plot the two graphs, Evelyn?
Yep.
Okay, thank you. Next is gonna be Christina. I don't see Christina here. Okay, so next is Queen Castaneda. Did you plot the two graphs, Queen?
Yes.
Okay, no problem.
No issues.
Okay, thank you. Emily is not here, right? Isabella is not here. Gabriela is not here. Princess?
Yep.
Did you plot the two graphs, Princess?
Yes.
Okay, do you have any questions about the graphs?
Yeah, for my graph, is it okay I start the minimum? What's it like you know how you said we have to minimize the space so like there's no space on the graph? I had the x-axis, the numbers start at 0.4 to minimize that spacing.
0.4?
0.04.
0.04. Let me see. Yeah, I think it's okay. What's the largest number in the graph there for you?
The largest number, I have it at 0.16 or like 0.17.
Let me see how it looks like. Your group number 6, right? Let me see. Sometimes your group number 6. Let me plot your graph here. I don't think it's a problem, but let me plot anyway. This one here, right? Or
Yeah.
this one or the previous ones? The second graph you're referring to, right?
The second graph.
Okay. 0, let's see here. 0.04, and then I gotta change the number from scientific to number to decimal places. Why is not showing 2 decimal places? Let's try again. It's not showing 2 decimal places. Why is that?
I think it's because you have your minimum at 0.004 instead of 0.04.
Really?
Yeah.
Let me see. Let's put 0. Let's put 0 first. Right? Now, number. It's supposed to show 2 decimal places, but it's not doing that. Why is that? That's shouldn't be. Yeah, it's start 0.004 again. Okay, let's see. Okay, now it's fixed. Okay, now it's fixed. Okay, now we start with 0.04, right? Yeah, that's okay. That's okay. Start with 0.04. Make sure you eliminate also. Start at 1, right? And let's see, 6, 8. Let's see the last one. Yeah, it's okay to go to 0.2 as well.
Okay.
Yeah, it's okay. Okay.
Okay, thank you.
Welcome. Kimberly, are you there?
Yeah.
Okay, were you able to plot the graphs, Kimberly?
Yes.
Okay, any questions about that?
No.
No? Okay. So, Trin. Okay, I'm not currently able to do it. Okay. Do it yet. Okay, try to get let me put just an N here. Make sure you can get to plot your graphs. Okay, Trin. Stefan.
Yeah.
Okay, did you plot the graphs, Stefan?
Yes, I did.
Do you have any questions? Any difficulties?
No questions, no problems.
Okay. So just
Thank
like I said, just like I said, I use Excel to plot my graphs. Okay. When I'm writing proposals, when I'm writing technical reports to get money from the government and other agencies, I use Excel, Microsoft Excel. I put that in my reports and things like that. Okay, so Jeremy, are you there? So it's very important that you learn how to work with Excel. Did you plot all the 2 graphs? Yet? Okay, that's good. Any questions? No? Okay. So see, we're getting to the point where we're gonna have our break, right? Let's go another 2-3 minutes and then we have our break. Paola, did you plot your graph, Paola? Almost done? Okay, good. Are you having any difficulties with that or is that straightforward for you? Okay. Okay, thank you. Next is Pedro Lopez. Pedro Lopez. I don't see Pedro Lopez here. Next is Isabel Medina.
We're still working on it.
She working on any problems?
No.
Okay, good. So
Thank
next is Aryan. Aryan, did you plot your graph, Aryan?
I haven't yet.
Okay,
I
you're
was
working on
trying
that?
to, yeah, I need more time.
Okay, so put it here working. Let me sort that out by group members. Data, sort, group number. Good. Next. Arwa, did you manage to plot your graph? Arwa?
Not yet. I'm still
Okay.
working.
You're working, okay. Gabriella didn't come, right? So you're working on your own, is that right?
Yeah.
Okay. Catherine Perez. Catherine is not here. Nadia,
Yeah, I did it.
you did it, everything? Okay, good. So there's more to do, okay? There's more to do. If you took my course in Physics 6, you know what to do next, right? If you didn't take, oh, I'm going to tell you what to do. Jason, did you plot your graph, Jason?
Yes, I plot my graph.
Okay, good. So any questions about that?
I'm good right now, thank you.
Okay, very good. Dana,
Yes.
you plot your graph?
Yes, I did. Just finishing up.
Okay, good. Any questions or you're good?
No.
Okay, then next, Ramon. Ramon is not here, right? Nope, Ramon is not here. Audrey? Oh, 5:10. Okay, so let's take a break, right? And then when we come back, I'll go talk to Audrey. Yeah?
Professor, I actually have to go right now. I just have a problem making a subscript.
Uh-huh. Okay, cool.
Other
Come
than that,
by.
everything's good.
Yeah, okay, so come by during my office hours and I'll show you how to do the subscript. Okay?
Okay, thank you.
Okay, so let's take our break right now. Break. That's gonna be 11 a.m. to 11:26 a.m. Let's see, someone left a message here. Juan Torres. Okay. Okay, so I see you in the next 15 minutes. Okay, thank you. I'm back here. Okay, and now we can get into the new material that you're going to need to finish this lab. Okay, so we did the following. Summary so far, right? Summary so far. We plotted two graphs. Next, you will have to document the units. You have to document the units of each parameter, right? In the spreadsheet. We do that in any paper that we write, in any technical document that we write, we have to do that, okay? So, and you already have some of the work done for you, okay? Because look here, for this part of the table, I already put the units for you, okay? Units, here you go. Volt, meter, and meter, right? And all you have to do is to fill up the rest. Okay? Not difficult, right? Here is the average value of X and the average value of the voltage, right? So you gotta get the unit of the average value of the x coordinate and the unit of the average value of the voltage. Okay? Don't put parentheses, just put like I put it here. Okay, don't worry about the resolution, okay? This thing is something that you don't have to worry about. Now, what about here, right? What about here? Are you familiar with this? Let me zoom in a little bit more. You should be able to see because you have your own spreadsheet there. Okay, this symbol here is the Greek letter sigma. Okay, we are using the sigma for conductivity, right? But it's not conductivity in this case. In this case, it's something else. Let's see. I want to zoom in now. Here you go, zoom. 200. Sigma in this case stands for standard deviation. Okay, standard deviation of your measurement. Let's see what the standard deviation that we are calculating here. You know, STDEV, right? STDEV. See, I'm calculating the standard deviation of the first X value. Okay, of the first equipotential of X. Okay, that's what it is. Because it's for the volts, for the 2 volts, for the equipotential of 2 volts, okay? The next standard deviation is going to naturally be the standard deviation of the X position of the 4 volt value, okay? And so on. You get the idea? So you have to tell me what's going to be the unit of the standard variation, of the standard variation of the X coordinate. Okay, and in order for you to know that, you must know the equation of the standard deviation, right? You must know the equation of the standard deviation. Let's take a look. Do you remember the equation for the standard deviation? Shouldn't be difficult, right? Hopefully you have even memorized it. I'm going to tell you there are all sorts of statistical parameters out there. Okay, the one that you were most familiar with, and also the first one that we learned, what's the first statistical parameter that we ever learned? Huh? What's the first statistical parameter that we ever learned? Anybody want to try it? The very first statistical parameter we ever learned is the average. Okay, here's the equation for the average. And that's one of the statistical parameters that we are looking at in the spreadsheet. Okay, it's the summation of every value divided by the number of values. Okay, we usually abbreviate by like a X bar, the average of a given value. We abbreviate like X bar, but some books also write that as being XAVG. Some books also write like that. Okay, and here's the equation. Okay, if you do the dimensional analysis of this equation, you'll be able to find out what is the unit of the average of a quantity, right? The unit of the average of different coordinates, different positions, is going to be the meter, right? The unit of the average of a voltage is also going to be a voltage in volts. Now, what about the standard deviation, right? We talked about the standard deviation. That's the equation for the standard deviation. It is the x1 value minus the average square summed with the x2 value minus the average square, Okay? Divided by what? divided by the number of data points. Okay? That's the equation for the standard deviation here. And we still have the square root. We still have the square root. Okay? And again, I want you to do the dimensional analysis of the unit to get the unit of the standard deviation. Let's see, someone left a message here. Evelyn. Yes, all my classes are posted in YouTube, okay, Evelyn? All my classes are posted in YouTube. So I have been posting those classes in YouTube since you can even access my classes that I taught the other semesters, okay? If you want to get ahead of yourself. But that's the idea here, okay? And so that's the equation for the sigma. And now from this equation, you will be able to find what's going to be the unit of the standard deviation of the position. And then, so you have the average, you have the standard deviation, two important statistical parameters. Then there is another type of standard deviation that we call standard deviation of the mean. It's abbreviated as sigma x. Okay? And that's what we have right in here, right? This one. I don't want this one. I want the other one, maybe. Yeah, here you go. Yeah, sigma x right in here. Sigma x. Okay? Standard deviation of the mean. Okay, is going to be that formula that you saw. This one here, okay? Is the standard deviation divided by the square root of the number of data points. That's how it is defined, okay? The standard deviation of the mean is used as an error of your measurement, okay? It's usually taken as being the error of your measurement. So if you're going to write down the value of a given measurement, of an average of a given measurement, you write down the average plus and minus the standard deviation of the mean. So go ahead, check what would be the unit for this standard deviation of the mean. And then the next one, what's going to be the unit of the ratio, right? Of the ratio of the standard deviation and its average. What is the unit of the ratio? How I'm gonna let me see. What's the unit of the of the following parameters better? Of the following parameter. Okay. And I also have the sigma x over x average. Okay, and there's a reason why I have that. This ratio usually is going to be very small. The smaller this ratio is, the smaller the error in your measurement. And I want you to find out what's going to be the unit of this ratio. Right? Look what the unit is going to be. The unit of the standard deviation of the mean, you already know this is the meter, right? The unit of the average of the position x is also going to be the meter. When you divide meter by meter, you get the number one. It's actually this number one, right? Is a unitless unit. Okay? There are many measurements out there that are unitless, that has no unit whatsoever.
Can you explain that one more time?
you know, this ratio that you see right in here, right? If you want to find out the unit of this ratio, what you're gonna get it? You're gonna get the unit of the standard deviation of the mean divided by the unit of the mean, right?
Yes,
Which is meter divided by meter, right?
correct.
So when you meter here, cancel out this meter, right? And what do you end up having? You end up having a
One.
number one, right? The number one. Okay?
Mhm.
Okay, this number one, what does this number one tells you? This number one tells you that the above parameter has no unit whatsoever. Okay? And this unitless unit is represented by the number one. Okay? And we have a bunch of parameters out there that are unitless. Okay, so if you're going to write the unit of this ratio here, all you have to do is to write here the number one. And you're going to find out many units out there that's going to be unitless, okay? You're going to find out many units out there that are going to be unitless. Examples, right? Let me give you some examples. Examples of unitless parameters, right? The first one, a unitless parameter, is the angle in radians, okay? By definition, okay? By definition, the angle, an angle, right? An angle. What's the definition of an angle? Is an angle, let's see, let's put it this way. An angle is defined as being, you know, the length of an arc divided by the radius of a circle, right? That's the definition of an angle. If you have a circle, let me get a circle here for you. Here you go, circle, right in here, right? Suppose that you wanna know the angle subintended between this point here and this other point right in here, right? How do you calculate this angle? The way you calculate this angle is by measuring the length of this arc divided by the radius of the circle, right? That's the very definition of angle, but angle in radians, right? When you divide one length by another, you get a unitless parameter. Okay? It is a unitless parameter that, by the way, we call it as being the radian. Okay, but the radian, strictly speaking, is a unitless parameter, a unitless unit. Okay, that's one example of a unitless parameter. Another one that we saw today was in today's lecture. Let's go there. What's the name? Is there? Do you remember? We saw today a unitless parameter, a parameter that has no unit. Is the dielectric constant, right? The dielectric constant has no unit whatsoever. Another example. Oh, I'll go back here. Another example of a unitless parameter is the dielectric constant we saw today. Okay? It has no unit whatsoever. And there are others, okay? And there are others. This ratio, for instance, is another example. The above ratio, sigma x over x average, is also a unitless parameter, and so on. So every time that we have a unitless parameter, so every time we have a unitless parameter, you must write the number 1, okay? In its respective cell, The only exception to this rule is going to be when an angle is measured in radians. Then you write rad for radian, okay? That's what you have to do, right? The next step, that's what you have to do. You plot the two graphs, and next you are going to write down all the units that you find here in these tables. There are units here. There are units here. Let's see if we have more. And then we also, let's see, we don't have units in this table. Okay, but we do have units right here in those two cells. Okay, see, numeric value here, unit here, the slope and the electric field. That's what you have to do in all my labs. So let's see, let's go back to what time is that? We are running out of time, right? 4 more minutes to go. It doesn't look like we'll be able to finish lab 1 today. Okay. So what you have to do? 1, plot 2 graphs. 2, fill up the units in the table, in the spreadsheet. The units of the parameters. The units of the parameters in the spreadsheet provided. Okay. 3, what else do we have to do? Now, I want to cover that today. It doesn't look like I have time, okay? You have to display the proper number of significant figures. Okay? Proper number of significant figures, okay? If you took my course, Physics 6, right, you already know. If you took my Physics 6 course, you already know that 1, any measurements with the ruler should be written up to the decimal place of the millimeter. Here in this course, I use the resolution of the instrument to determine the number of significant figures, right? Okay, in this course, I use the resolution of the instrument to determine the number of significant figures of a given measurement. Okay. So let's take a look here. One example, right? One example right in here. X. So those X and Y's coordinates were measured using a ruler. Okay. And the ruler has a 1 millimeter of resolution. So the proper way of writing down the proper way of displaying this measurement would be to right click, format cell. We're going to put it in numeric format, not in scientific format. And then, because the unit is going to be the meter, we have to display up to the third decimal place, which is the millimeter. Okay? So this measurement here that we have, the proper way of displaying it would be to display just like that, up to the third decimal place. Okay? 0.045. Make sense? Okay? You might have learned in a different way, okay, but I prefer to make it simpler this way. Just use the resolution of your measurement. This one here, same thing. Right click, format cell, display it in numeric format up to the third decimal place. And that's the right way of displaying this measurement. And by the way, everyone here is going to be the same. Format, numeric, 3 decimal places, which corresponds to the millimeter. Okay, that's just for the ruler. Let's stop now. Next time we have to continue because there are more things that we have to cover. Okay, the lab report's not due yet. We have to cover more stuff before I can make it due. Okay, next week we're gonna have an exam, so don't worry about the lab report yet. Take all your time to study for the exam, and I see you next Monday. Okay? See you then.
Thank you.
Thank you.
Bye-bye.
You can say. Okay. Can you be able to change the times now, like you did in the beginning of a few hours before class started?
Let's see. Are you talking about the exam?
Yeah, the times, because you said now it's 9:40 to 11:40.
Yeah, that's right. You want me to put that in the canvas, right?
Yeah, so that I could be.
Yeah, let me go there. Let's see if I can do that.
Okay, thank you.
Canvas. Okay, let's see. Okay, thank you. Okay, so let's see. Course, this one. Now we're going to do quiz. All quizzes available. I have to create the first quiz. It's going to be a classic quiz. Okay, it's going to be exam 1. And let's see here. Time limit is going to be 120 minutes. Let's do. Require. Okay, the due date is going to be 11th. What time? It's going to be 11:40, right? 11:40 a.m. 11:40 a.m. Right? Available from May 11, 9:40. Can you still see my screen, Ani?
Yes.
Okay. Let's see. Let me stop recording too.